All right, so today we're going to talk about E2 elimination, Zaitsev's rule, the E1 mechanism, and hopefully get into stereochemistry of elimination reactions. On Wednesday, we have an inverted lecture, okay? We're going to spend most of our time on that inverted lecture going over carbocation rearrangements. Okay, so you really need to be here Wednesday because carbocation rearrangements are a big deal, and keeping track of everything is kind of difficult. So it's not that it's hard, it's just that it's tedious, okay? And so I want to spend probably the first 20 minutes of class, maybe even the first full 30 minutes of class, talking about carbocation rearrangements. And so there should be a pen cast up available for that in plenty of time. So take a look at that. All right, so the mechanism of the E2 reaction, we know that the kinetics are second order, right? Meaning that the rate of the reaction is going to be dependent on two things. What are those two things? Concentration of the base and the concentration of the alkyl halide, right? We know that it's a single-step mechanism, meaning that all bonds that are being formed and broken are all happening at the same time. So it has that single transition state, that single hump in that energy diagram. We know that the more substituted halides react the fastest. We know that it's favored by strong bases, and we know that it's affected by leaving groups. So the better the leaving group, the better the reaction. And we know that it's favored by a polar aprotic solvent. A lot of this stuff sounds very familiar to what? SN2, with the exception of what part up there? Okay, we have bases instead of nucleophiles, that's right, and what else? And the substitution order, right? In an SN2 reaction, it's primary is better than secondary, right? But in the E2 elimination, it's exactly the opposite. Tertiary over secondary over primary, okay? So, real quick, rank the following order of increasing E2 reactivity. In other words, if I just did this experiment that we did just a few minutes ago with these three substrates in an elimination type of reaction, which one would turn colorless first? The one in the middle. And why would the one in the middle? Because it's a tertiary. Okay, so we know that tertiary alkyl halides react faster in the E2 reaction, so that's good. What would be next? Okay, and because it is a secondary, followed by the one on the left, which is a primary. Okay, very good. All right. And so E2 eliminations, we talked a little bit about this in the past, are pretty useful. For example, they have taken this primary alkyl halide and treated it with, what is this? This is a polar aprotic solvent, that's right. We'll talk about that in a second. But what about this? Salt. It's a salt. What salt is it? It's a bulky one. It's also a base, right? It's a bulky base. So is it a nucleophile? That's right, it's a non-nucleophilic base. Why is it important to use a non-nucleophilic base here for this reaction? That's right, because it's a primary alkyl halide, right? It could also undergo SN2 type chemistry if we used an inappropriate base. So we use a big bulky base here so to keep the nucleophilic chemistry down to a minimum, essentially eliminates it. And DMSO, does anybody remember what that stands for? Dimethyl sulfoxide, and it is a polar aprotic solvent. Okay, and so all this favors the E2 elimination. So we do an E2 elimination here, we get the carbon-carbon double bond that they're after, and then after several steps they take this and convert that into quinine, which is used as an anti-malarial drug, right? What's DBU? I'm not asking you to tell me the name, but what is DBU? It is a base, but more specifically, it is a non-nucleophilic base, and it is also, is it neutral or charged? It's neutral, so it's soluble in organic solvents, right? Although they don't have the solvent listed here, but it is a non-nucleophilic base. It's one of them that we mentioned during the last lecture. What other non-nucleophilic base that starts with D and B did we have? DBU and DBN, right? And both of those are non-nucleophilic bases. Again, getting the E2 elimination to give us the carbon-carbon double bond, and then after several steps, taking this to get us estradiol. Where are these rings in the product? Can anybody tell me? Right here. That's right. So this was very important in these hormone-type syntheses that have been important over the years. Okay? Now, up until now, we've really kind of stacked the deck in our favor. All the beta carbons were identical, right? So you either had only one beta carbon or all the beta carbons were the same. And so it really didn't matter where the hydrogen came from in that beta elimination. If only life were that simple, right? In this example, you'll notice we have three beta carbons, but two different ones, right? You'll notice that the beta 1s are identical. They're both secondary, right? There's a mirror plane that runs through here. That's why beta 1 and beta 1 are identical and labeled as such. But we also have beta 2, right? And so if we run this reaction and do an E2 elimination, we would expect to get two different products. The product where we lose the hydrogen from beta 1 and the halogen to give product A, or where we eliminate the hydrogen from beta 2 and the halogen from the alpha carbon and get product B. Okay? Notice the major product and the minor product. Would you have predicted that before I showed you this? What would you have predicted? Based on probability, what would you have said? Not that. That's true.
Well, you'd think that some either might still have the I or something would be different. You wouldn't think that both the things would be gone.
Okay. How many hydrogens collectively do I have on the beta 1 carbons? 4. There's 2 on each carbon, but a total of 4, right? And how many on that methyl group? 3. So if we're just playing statistics, what are the chances of abstracting from beta 1 over beta 2? It's 4 to 3, right? I've got 4 opportunities to abstract a hydrogen from beta 1 and only 3 opportunities to abstract a hydrogen from the methyl group, right? So you might predict that beta 1, right, would be 4/3 more likely. Okay? And in fact, that seems to give us the major product. But is it just about statistics?
No.
What's it about? It's about science. A little more descriptive maybe there, Matthew? How about stability of the alkenes? Does that have any role to play here? Are those two alkenes of equal stability? No. What's our stability order? Roughly. Is a more substituted alkene more or less stable than a least substituted alkene or a lesser substituted alkene? More stable, right? Which one of these is the more substituted alkene? A, right? And so Zaitsev's rule, and it's actually spelled 2 different ways depending on which book you use. I always spell it with the Z, but some spell it with the S-A-Y, okay? Zaitsev's rule. Zaitsev's rule basically states that you're going to abstract the hydrogen from the beta carbon with the least number of hydrogens. It's going to lose, okay? And the reason that it loses is because when you abstract the hydrogen from the beta carbon with the least number of hydrogens, you actually end up with the most substituted alkene. It's all about alkene stability, okay? So A is the major product, B is the minor product, okay? And so this ends up being what we call a regioselective reaction. It's going to give us predominantly, exclusively, one constitutional isomer over the other. Okay, and so these E2 reactions are said to be regioselective. And when you have an abstraction at the beta 1 carbons, as it's shown here, this is actually the least stable transition state, and this is the more stable transition state by abstracting the hydrogen from the more substituted carbon, okay, or the carbon on the, or the beta carbon with the least number of hydrogens, however you want to think about it. Why would this be a more stable, and by more stable we mean lower in energy, right? Why would this be the more stable transition state? That is true.
Well, you got the big groups, so they're all groups kind of, I don't know, like you have the ethyl, the methyl, that's all close together on the top one, right? Much more distributed.
Okay. What else? What about the Hammond postulate? What's it tell us? Transition state, right? What's the substitution that's starting to be built up here versus here? As we're starting to form this carbon-carbon double bond, right, is this more substituted or less substituted than the one up here at the top? It's more substituted, right? And we know that more substituted alkenes are more stable. So that transition state, as it's building up that alkene carbon-carbon double bond in the transition state, right, that's more substituted, so it's going to do what to the energy of the transition state? It's going to lower it, right? And so it's all about that Hammond postulate stuff that we learned about earlier, right? So as we're forming this carbon-carbon double bond, we notice that this is more substituted. That's going to be the more stable transition state. It's going to lead to the more substituted product, and it's going to be the major product. What do you think in terms of a ratio of product C versus product D? Approximately, you think it's going to be 2 to 1, 3 to 1? How would you determine that? Where would you take a guess? What do you think, Jamie Lou? It's not a bad guess, right? You're probably going to be about 75% at least this when we call something a major product. It's usually not going to, we're not going to call something that's 55, 45 major minor, usually. I mean, yes, it is major and that is minor, but that's pretty close to 1 to 1. So yeah, I would predict this to be somewhere 3 to 1 or greater, okay? Kind of as a rule of thumb. Works pretty well, okay? Can anybody tell me why in this particular reaction we get this mixture and the major minors are as listed? Why is this the major product? It does have lower energy, but why does it have lower energy? That's exactly right. The trans product is more stable, right? Why is the trans product more stable? Allison, can you explain that again, please?
So the two big groups are all up in each other's face.
Here?
On the other one.
On the other one, that's right. So putting these two big groups cis to one another, they're crowding each other, right? And so that's going to be higher in energy, whereas this is going to be lower in energy because those two big groups, they can't really see each other, right? At least in terms of steric interactions. So this is a unhindered alkene, whereas this is a sterically hindered or encumbered alkene, okay? And so this occurs by an E2 elimination as well, okay? To give these so-called still being products, okay? So, what is the major alkene produced by the elimination from the following two? What do we do when we're thinking about the elimination? What's the first thing that we identify? Pardon? We identify where the leaving group is, right? And then we mark what? The alpha carbon. And we know that the hydrogens have to come from the beta carbons, okay? So what I do is I always identify the alpha carbon, and then I label each one of my beta carbons. And I'll write beta, 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 however many of them that I have, okay? And then I go through and I determine whether all the betas are identical or different, and then I'll label them beta 1, beta 2, beta 3, if they're all different. If they're all the same, I'll just label them beta, beta, beta. Why is that important? Why is it important to identify whether they're the same or different? That's right. Right? We got to follow Zaitsev's rule. So we know what the alpha carbon is here, right? How many betas do I have? I've got a beta and a beta. How would you label them? You can label it beta 1 and beta 2 or beta and beta prime. I don't care how you label them. You can call them roses and dandelions for all I care. Okay? The point is that you recognize that they are different. Okay? So what does Zaitsev's rule tell us? Okay, so if we label this beta 1 and beta 2, which one loses the hydrogen? Beta 1. And so what's the product? If I was to draw the product, what would the product be? So we know we're going to lose this, right? And we've got a hydrogen here, then we're going to lose that. So where am I going to put the double bond? That's right. In between these two carbons. Okay? If we were to eliminate from the other beta carbon, what kind of alkene would we end up with? Terminal, which is also a, we have monosubstituted, disubstituted, trisubstituted. It would be monosubstituted. And so we'd be looking at a monosubstituted versus a trisubstituted alkene, right? So this would clearly be the major product because it's,
Mono because it's only connected to one or
well, this is trisubstituted.
yes, so it has three things off it.
That's right. Whereas if we eliminate here, we'd end up with that. And so we only have the one group on the alkene. Does that make sense? How about for the second problem there? Where's my alpha carbon? Sam, where's the alpha carbon? Second one here. That's right. So there's my alpha, right? And everything attached to that's a beta carbon, right? So I've got beta 1, beta 2, beta 3. Are they all the same or different? They're all different. Beta 1 is what kind of group? It's a methyl group. It's a CH3. Beta 2 is it's a CH2. Those are also known as what kind of groups? If CH3 is methyl, CH2 is methylene. And what's CH? Methine. So we have a methyl, methylene, and a methine carbon. Okay? So which one of those loses the hydrogen? The methine. And so we end up putting a carbon-carbon bond between these two carbons. And what kind of alkene would we end up with? That's cyclic, that's true, but would it be monosubstituted, disubstituted, trisubstituted, tetrasubstituted? What would it be? That would be it, right? What is that? It's tetra. That's right. We'd end up with a tetrasubstituted alkene in that particular case. Okay? So, the E2... Okay? I look at both carbons of the alkene, right? And I ask myself how many carbon groups are attached to it. There's 1, there's 2, there's 3, there's 4. That's right. That's what Zaitsev's rule essentially says. We're going to get the most substituted alkene that we can. That's what Zaitsev's rule really is. Okay? So in E2 elimination, identify the alpha carbon, identify all the beta carbons. What kind of base do we want to use? Non-nucleophilic bases. What kind of solvents do we want to use? Polar A product. What's the rate going to be proportional to? Base in the alkyl halide, that's right. Now, E1 mechanisms follow a lot of the same rules that we talked about for SN1, okay? Oops. And so the rate of those reactions is going to be equal to some rate constant K times the concentration of the alkyl halide, okay? It's first order reaction kinetics, meaning that if Chance comes into the lab and adds twice as much base as Delaney does, who gets done quicker? They get done at the same time, right? Because the base doesn't come into play, right? So if they start off with both having the same amount in terms of concentration of the alkyl halide, but Chance just happens to add twice as much base, thinking he's going to get out and get to lunch a little quicker, turns out they end up being completed at exactly the same time, okay? He just wasted some base, that's all he did, okay? Because the mechanism is what rules it, because the rate determining step must be what here? Formation of the carbocation, that's exactly right. So if we look at an E1 mechanism, we know that the leaving group has to leave. We end up with a carbocation intermediate, right? And now, instead of having the water function as a nucleophile, how's it functioning? As a base. And so the water can attack the proton. Those electrons then go to the carbocation. We form the carbon-carbon double bond, and we get a little bit of acid, okay? So what's the difference here between this and the reaction we just did? Then here. How do I know that this went through SN1 chemistry and not E1 chemistry? Okay, water's a fairly decent nucleophile, that's true. What else? When I ran this reaction, how was I running it? What were the conditions? It wasn't heated, that's exactly right. It's at room temperature. And we know that substitution is favored or unfavored at lower temperature? It's favored, but elimination is favored by higher temperatures, right? So I know that this reaction most likely went through SN1 chemistry and not E1 chemistry because of the reaction conditions that I chose, okay? I also know it because I actually have done experiments to prove that I get mostly the alcohol. Now, if you paid really, really close attention to that, when I would kind of shake it a little bit, you would see little bubbles. So there was some elimination going on because this alkene, what do you think the physical state of this alkene is at room temperature? Solid, liquid, or a gas? It's a gas. And so some of the little tiny bubbles that you would get actually show that you do actually form some of this. So what does this tell us about E1 and SN1 chemistry? It's messy as heck. That's what it really tells us, okay? So usually you want to do SN2 or E2 chemistry most of the time. But there are cases where you'll want to do E1 or SN1 type chemistry, and you've got to pay really close attention to the reaction conditions because it matters. And so we could favor the SN1 chemistry here by lowering the reaction temperature, and room temperature is pretty low. What would I have done, Gabrielle, if I wanted to increase the amount of elimination? What would I have done in here? I would have brought in a hot plate, right? And I would have warmed up the solutions before I added the alkyl halides. And what's the rule of thumb for reaction rates in terms of temperature? What did I tell you? Okay, well, close. So for every 10 degrees I increase in temperature, I almost double the reaction rate, right? So if I had increased from room temperature to about body temperature, we would have expected to double the rate. So maybe I could have just held it with my hands for a while and warmed it up. Yep, 10 degrees Celsius.
Does temperature only really affect E1 and SN1, or does it for the...
Temperature affects all reactions, right? And in general, this is just a rule of thumb, for every 10 degrees you increase the temperature, you approximately double the rate.
So if you were to like heat up something that would go through SM2 or E2, it would do the same
It would do the same thing, approximately, right? That's why when you all run a fever, your body is actually, chemistry is actually occurring at an accelerated rate. You are decomposing at an accelerated rate. You know, you're dying faster. That's exactly right. That's why when you run really, really high temperatures, they don't worry about hypothermia and they throw you into a tub of ice water, right? Try to get that temperature down because it accelerates everything and it becomes a real problem, okay? So this should look familiar, right? This looks like an SN1 reaction profile. The only difference, right, is in the second energy of activation. The first is the same. The leaving group leaves, I get the carbocation intermediate. What's different is here. Instead of the nucleophile, water, attacking the carbocation, it doesn't function as a nucleophile. It functions as a base, and it attacks one of the hydrogens on the beta carbon. That's the only difference in this reaction profile, other than, of course, the products are different. But in terms of the transition states, the difference between E1 and SN1 is all in that second transition state. First transition state is exactly the same, which is kind of nice and convenient for you all because you only have to remember one thing, right? Good. We know that as we increase the substitution of our alkyl halides, we're going to increase the E1 reaction rate. And the reason for that is because we can increase the carbocation stability, right? So if I have a more stable carbocation, what does that mean in terms of the transition state? Higher in energy or lower? Hammond's postulate, right? So you didn't hear me? Okay. So if I have a more stable carbocation, what does that mean for the transition state of that reaction? More stable or less stable? More stable, right? More stable transition state. Why is that? Because that's what the Hammond postulate tells us, right? The transition state is going to look more like that carbocation, right? So if I have a more stable carbocation, that means it's lower in energy. That means that the transition state is going to be lower in energy, right? So we know that the transition state for this is going to be lower in energy than the transition state for the secondary, for example, okay? Here we have an example where we have a tertiary alkyl halide. Now wait a second, tertiary alkyl halide, doesn't that also favor E2 elimination as well? Yeah. So how do I know this one has to be an an E1 elimination? Water's the solvent, but it's also the base here, right? And is it a good base? No. So not so good bases also favor the E1 reaction. And Zaitsev's rule also applies to the E1 reactions. So if we take this, and instead of using sodium hydroxide, which would have guaranteed a what kind of reaction? An E2, we use just pure old water, which is kind of what we did here, right? A little acetone to make everything soluble, but pretty much so it's mostly water, right? Now we get our elimination to occur, and again we end up with the products. Notice again the more substituted alkene is favored in these reactions. Okay. So SN2 and E2 are well-behaved reactions. Well-behaved. SN1 and E1, they've got a mind of their own. Okay? Anytime you go into the lab and you say, I want to do an SN1 reaction, you got to stop and think about the possibility of elimination. Anytime you want to do an E1 elimination, you got to think about the possibility of doing SN1 chemistry. They're always competing with each other. And really what you can play with, right? You can play with solvent conditions. You can play with temperature. That's pretty much so it. Okay? You're always going to have a competing pathway. Okay? But usually you can force it one way or the other by playing with temperature pretty well. So if we want to do an SN1 chemistry, right, we've got the same intermediate as we would have in the E1. But here the nucleophile, of course, is going to attack the carbocation, whereas here it's going to function as a base and abstract the proton. Okay. Now let's talk a little bit more about the E2 reaction. E2 we know is a single step, right? Not all hydrogens that are on the beta carbons are actually reactive. Okay? And it turns out that if you have a hydrogen that is syn paraplanar to the leaving group, those are unreactive. They don't react. Whereas if the hydrogen is anti-periplanar to the leaving group, they are reactive.
What is syn paraplanar exactly?
They are syn to one another. So they're in the plane of the board, but they are syn to one another, or cis if you will. Here they are anti to one another. If you look at the, huh? Kind of like it, but you're really looking down the carbon-carbon bond at the Newman projections, okay? The anti-periplanar hydrogen actually is the one that's reactive in an E2 elimination reaction, okay? So that's going to determine which conformation of a molecule is going to react. This is why we went through all that conformational analysis business, right? So we looked at all the conformational analysis. We know how to draw our Newman projections. We can determine which hydrogens are anti-periplanar to the leaving group, okay? Now, if we think about it very simply, we know that halogens, right, have lone pairs of electrons around them, so they're electron rich. And a base, by definition, has at least one lone pair of electrons, right? So if we think about this in an oversimplified fashion, it makes sense that the base would not want to come close to the leaving group. And so that's why it would attack an anti-periplanar hydrogen atom. Whereas if we brought the base, which has got lone pairs of electrons close to the halogen, we'd get those electron pairs repelling each other, right? And so that's why we can argue that it's not going to go after the syn-periplanar hydrogens. But there's more to it than that. What is the more? Okay, hybridization. What else? So what's happening to these electrons in this carbon-hydrogen bond as the base comes in and reacts? Where are they going? What's happening to these electrons? How would you push that on paper? What do you think, Nathan? Where are these electrons going? They're making the pi bond, right? So they got to come in on the opposite side and push the leaving group out, right? That's how they're working. That's an orbital argument. Can they do that here? Can they come in around from the backside and push that out? No, those electrons would have to go on the same side as the leaving group, and we know that the orbital alignment just isn't right for that, okay? So yeah, we can think of it pretty simply as just electrostatic, like charges repel each other, but that's overly simplified. Now it works, and if that's what works for you, keep it in your head, okay? But the real reason is because this electron pair that's this carbon-hydrogen bond, those electrons are going to go to form the pi bond, and they've got to come in and kick that leaving group out. They've got to enter that anti-bonding orbital for that halogen carbon bond, okay? Now, if your molecule is acyclic, that is linear, okay, you've got free rotation. And so you can always get one of those hydrogens to be in a conformation that's anti-periplanar to the leaving group. However, in a ring system, that's not always the case, okay? And if we have chlorocyclohexane, for example, right, we know that we can have the chlorine in the equatorial and the axial position. And we know that the equatorial position is the most stable, right? Why is that? No 1,3 diaxial interactions. We want the bigger group to be equatorial if at all possible, okay? However, if we look at that, are any of the hydrogens anti-periplanar to that carbon-chlorine bond? If we were to look down this carbon-carbon bond or this carbon-carbon bond, is there any hydrogen that is anti-periplanar to that carbon-chlorine bond? What do you think, Rose? Tells us that no reaction occurs, right? So are any of those hydrogens anti-periplanar to that carbon-chlorine bond? No. So the more stable conformation of chlorocyclohexane actually can't do elimination chemistry at all, okay? At least E2 elimination chemistry. But if we ring flip it to the less stable B, where we have the chlorine in the axial position, now what do we see? This carbon-hydrogen bond, right, these electrons are anti-periplanar to the leaving group. so it can react. Okay? So using Le Chatelier's principle, how can I convert all of chlorocyclohexane into cyclohexene by E2 elimination? How does that happen? If it's only this that reacts, how can I get every bit of my chlorocyclohexane to become cyclohexene? Well, there's not enantiomers here. There's no stereocenter, right?
You find some way to make it go from the more stable wording to the less stable wording, but
Okay, it's only this that reacts, right?
you find some way to make everything flip.
So do I have to do that? So if I can, this is an equilibrium process, right? So if I affect this side of the equilibrium, what happens? That's exactly right. Le Chatelier's principle works. So this is the only conformer of chlorocyclohexane that undergoes an E2 elimination, and that's what gives me my product, right? And as I deplete this, what happens to this? It ring flips, right, to get back to the equilibrium. And so by pulling this out of solution or whatever, we could draw the reaction all the way to the right and do the elimination.